Good evening, students. Today I'm just gonna take you a step ahead from the discussion what we had in the last class. Okay, so first of all, let me see you guys and how many of the people here. Just let me find it out. Say hi here. So Lokesh Parab, hi. Kirti is here. Ritik Raj is here. Yeah. Good evening. Lokesh or Kirti, could you please give me an idea what happened in the previous week so that from there I will push it forward? Am I audible and visible? At least if not visible, am I at least audible? Hey guys? Yeah, you guys are there. Fine. Anyhow, I guess I am discussing a topic that is CPU design. In the CPU design, I discussed about. Yeah, Kirti, I know that you didn't attend the last session, but anyhow, Lokesh was there in the previous session. I just wanted to know what happened in the previous session. But anyhow, I just guessed that the last session was all about, if I'm not wrong, I was discussing a few good questions. Didn't I? Lokesh, are you there? Let's respond. At least, Kirti, could you please, tell me what was your previous session? In your previous session, in fact, what happened? Yeah, due to network issue, fine, doesn't matter. But in your previous session, what happened? I just wanted to know. Okay, anyhow, let me, just recollect it by myself, and I'll explain you. I think we finished instruction formats. Yes. I was, giving you an idea about the instruction formats. In the instruction formats, in fact, I explained you guys about memory reference instructions and register reference instructions. Yeah, exactly, Lokesh. Yes, you're right. In fact, I was giving you the details about the register reference instructions. So I will give you a small revision, a small recap, what happened in the previous week, so that other people will also be able to understand. I was, explaining you guys about the different instruction formats that are available in the computer system. Okay. Here. Here we talked about the instruction formats with respect to the location of the operand and a number of operands. In the last week, I talked about the register reference instructions. Right? In the register reference instructions, the operand will be one of the processor's register itself. Right? That is, when it comes to the register reference instructions, the operand will be collected from one of the processor's registers. That is, in the memory reference instructions, I will show you right now. Yeah, here. You can see here, that is, there are in fact three different instruction formats. One is memory reference instructions, the AND, add, load, store, BUN, BSA, ISA. All these are just nothing but the memory reference instructions. For these instructions, operand is available in main memory, and for the the download instructions, these set of instructions, as you can see, the bottom portion of the screen, that is CLA, right? From CLA, all these instructions, for all these instructions, the operand will be the processor's register. In fact, it is accumulator, one and only accumulator. CLA stands for clear the accumulator. CLE stands for clear the extended accumulator. You know what is CLA? You know what is clear operation? Clear operation means the contents of the accumulator will get cleared when this instruction gets executed. CLE stands for the contents of extended accumulator gets cleared the moment this instruction gets executed. CMA stands for when this instruction gets executed, contents of accumulator will get complemented. You know what is complemented? 1 to 0, 0 to 1, right? The 1 would turn to 0, the 0 would turn to 1. Okay, that is CMA, complement accumulator. Is the screen visible for you guys? Is the screen visible for you guys? Kirti and Lokesh and the Kalpana. Yeah, hi, good evening. Okay, fine. When it comes to CIR, listen to me, the guy who did not attend last week, Kirti. CIR stands for circular shift right. You know what is shift operation? Just no. Tell me quickly, do you know shift operation or not? So that I'll be able to know whether you've got an idea about the shift operation or not. Kirti, just tell me. What is shift operation? Do you have any idea? Good. Oh, no. Kirti, fine. I'll tell you. Okay. Here itself, I'll tell you what is a shift operation. Let us say that the content of the accumulator is 1101. Okay. Let us say accumulator is a 4-bit register right now. For this instance, I am taking an example that the accumulator is of 4 digits, 4 bits. Now, prior to performing the shift operation, the contents of the accumulator is 1101. Okay. Now, after performing the shift operation, when I perform a shift operation, this shift operation can be performed in 3 ways. One is towards the right, which is called a right shift. One is towards the left, which is called a left shift. One is, the contents of the register will be circulated among themselves, which is called a circular shift. Okay, during, let us say, right shift, 1101 must be shifted right. What happens during the right shift? Try to understand. Every bit will move to the next significant bit position towards the right direction. That means this digit will come here, this digit will come here, this digit will come here, this digit will be discarded. Okay, so I'll tell you that 1101. After shift, this 1 will come here, this 1 will come here, this 0 will come here, this 1 will be left over. Okay, and there is a bit position 0 here, there is a bit position which is left here because during the shift, the most significant bit moved to its right. Did you get it? So the most significant bit position is empty. So in that bit position, we will put a 0. This is what the right shift. I hope it gives you, some sense, because shifting is a very simple process in which each and every digit will move to its right direction when we perform a right shift. Next, right bit position. When we perform a left shift, let us say that 1101 must be shifted left. So what will happen? This 1 will come here, this 0 will come here, this 1 will come here. Okay, and in the final bit, this is the most significant bit, will be left over. Okay, as we are moving the bits towards the left, this least significant bit will be empty. In that bit position, we will put a 0. This is what right shift and left shift. Did you understand? Yeah, this is what right shift and left shift. But there is another shift called circular shift. What is circular shift? I will put it here. When circular shift is performed on accumulator, which is equal to 1101, then the contents will be circulated. That is, we are not going to lose any bit here. Rather, the contents will be circulated among themselves. So we'll observe what is going to happen during a circular shift. Let us say we are going to perform circular shift right, meaning this position, right? So what will happen is this one will get circulated and will come around, and it is going to occupy the first bit position, and then this one move to the right position, this one will move to its next right bit position, this 0 will move to its next right bit position. So in which the total content will be like one will be the first bit, next one, it will be 0. Okay, I hope you got it, because this one got circulated and it occupied most significant bit, and then this bit moves to its right, this bit moves to its right bit, this bit moves to its next right bit position. I hope you got this thing. Similarly, left, circular shift left. During the circular shift left, what will happen is this 1 will come here, this 0 will come here, this 1 will come here, and this 1 will be again circulated back to this bit. Okay, so this is called circular left, this is called circular right. I hope it gave you enough idea how a shift is going to be performed. A particular shift is going to be performed. Either it could be a right shift or a left shift or a circular shift. I think you got it completely. Did you? Yeah, that is what the shifting is all about. When we perform CIR, when the instruction is CIR, circular shift right will be performed on accumulator. Circular shift right will be performed on accumulator. Okay. When we performed CIL, circular shift left will be performed on accumulator. Did you get it completely? You're listening? You guys are there. You just have to participate. Good, good. Now, during when CIL gets executed, a circular shift operation, circular shift left operation will get performed on accumulator. That's it. What is INC? INC stands for incrementing the accumulator. The contents of the accumulator will get incremented. When this instruction gets executed, INC, the contents of the accumulator will get incremented. Okay, and then SPA. What is SPA? Try to understand. SPA stands for skip the next instruction if accumulator is positive. Okay, this I will explain you by using an example. Anyhow, I covered it in the previous week, but I'm going to explain you once again in a nutshell. Here. Now, what we'll do is, we will see how SPA instruction gets executed. Let me take the help of main memory once again. In main memory, let us say this is my main memory, and the current instruction is at an address 43. The next instruction will be at 44, and the current instruction is SPA. Okay, for this instruction, next instruction is 44, means program counter holds an address that is 44, right? So let us see what is going to happen when we execute SPA. SPA stands for skip if accumulator is positive. Okay, so which means that we are going to check the contents of accumulator. If those contents are positive, then the next instruction will be skipped. Next instruction will not be executed. Rather, next to next instruction, 45th, will be executed. For that, we are going to watch the contents of the accumulator. The contents of the accumulator will be either positive or negative depending on the most significant digit. The most significant digit, if it is equal to 0, then the contents are positive. If it is equal to 1, then the contents of the accumulator will be negative. If the accumulator is positive, next instruction will be skipped. 44th instruction won't be executed. Rather, 45th instruction will be executed. Similarly, there is one more instruction called SNA. What is SNA? SNA stands for skip if accumulator is negative. Okay, next instruction will be skipped in the case if the accumulator is negative. Okay, earlier when the accumulator is positive, next instruction is skipped. Now when SNA gets executed, if the accumulator is negative, then the next instruction will get skipped. That is what the meaning of SNA. And the third one is something called SZA. Needless to explain what is this SZA. Of course, as you interpret it, that when the accumulator is equal to 0, then the next instruction will be skipped. Otherwise, next instruction won't be skipped. There is one more instructions which is similar to this, that is SZE. What is SZE? Skip if the extended accumulator is equal to 0. You know that extended accumulator is an additional digit to accumulator. If you could remember, actually our accumulator is of 16 digit, right? Okay, accumulator is equal to 16 digit. But we provided the accumulator with an additional digit to support when accumulator is overflowing. When accumulator will overflow during an addition or any arithmetic operation, the accumulator might receive a 17th digit, right? Because we can't get any guarantee that the result when we add two operands will only be 16 digits, which is equal to accumulator. Sometimes the result may cross 16 digits, it may go to even 17 digits. When the result is equal to 17 digits, we are in a situation called carry. So in order to support this carry, we used an additional digit which is called extended accumulator. I explained about extended accumulator in one of the previous classes. Rather, in two of the previous classes, I stressed on this extended accumulator, if you could actually remember. Do you remember? This extended accumulator is a 1-bit register. You there, Lokesh? You there, Kirti? You remember what is this extended accumulator? Yeah, whatever. This extended accumulator will be cleared. Rather, this extended accumulator contents will be checked. If the contents are equal to 0, then the next instruction will be skipped. That is simply the definition of SPA, SNA, SZA and SZE in short. Okay, so simple. Next instruction will be skipped in the case of accumulator is either is positive or negative or 0, or if extended accumulator is 0, depending on the instruction that is being executed. Okay, so that is it. So then there are a few more instructions which comes under register reference instruction. That is the final instruction called halt instruction. Okay, Lokesh, I guess you got completely what is the halt instruction, right? I just want Lokesh to answer one question. Are you there? Okay, fine. If the current instruction is a halt instruction, let us say, yeah, let me draw once again the memory. Yeah, the current instruction, let us say it's a 23rd instruction. The current instruction is halt instruction. So what will be the program counter's value for this, halt instruction? I want Lokesh to answer. What is the program counter? No, of course, Kirti can't answer because she did not attend the previous session. If you could answer, I'm going to give her an idea how the program counter is going to be decided, is going to be updated for a halt instruction. I just want your answer. What is the program counter value when the current instruction is a halt instruction and the current instruction address is 23 right now? Yeah, just answer them. What is PC's value? Yes, of course, it is 23 only. Kirti, excellent. I don't know how you got the answer. When there is a halt instruction, we must be sensible. Halt is a situation called. Are you here? Halt is a situation in which the computer system will be halted, right? If the computer system is halted, then there won't be any next instruction. You got me? So this is what the halt instruction is all about. So generally the halt will be executed whenever the computer system doesn't have any more program to follow. Okay, so only for the halt instruction, current instructions address and both program counters value and the current instructions address, one and the same. Okay, it is, yeah, very good. So for the halt instruction, both current instructions address and the program counters value will be one and the same. If you could understand this, we are done. I'm going to solve a few good gate questions after this. Are we done? Are we ready to solve a few gate questions on this? We will solve a few gate questions on this. Yeah, fine. Now, just meanwhile, what I'll do is, I will tell you one of the previous gate question. I will tell you in which year it was asked. So what you do is, you just search the net and get the question by yourself, so that it saves some time, so that I don't need to write it on the board, on the screen. Yeah, this question was asked in GATE, what do you call, 2007. This question was asked in GATE 2007. The question starts like, consider the following program segment. I will show you the question. Let me go to the next. GATE 2007 it was. Is it copied? Yeah, yes, it is copied. Just a minute. This is the question. Meanwhile, what you do is you just you know look at this question and try to note down this question. Otherwise, you just can directly copy it from the net, because in the net every question is available. The question starts with, consider the following program segment, and here R1, R2, and R3 are the general purpose registers. So that I would start explaining this question. This is one of the important questions. If you could understand this question, how to solve this question, then lots of the things will be made easier. Most of the questions from the instruction set architecture may look like this. So what I expect you guys is just at least stay focused on this question. Even if you can't solve this question on your own, at least while explaining, you just stay with me. Okay, don't go here and there, so that I'll be able to explain you in a better way. I just request you people to be with me all the time. Okay, so I'll copy this. Will it get copied or not? Okay, this is copied. Yeah, this is better. Now look at this question. Is screen visible? Is the screen visible right now? Of course it is visible. So look at this question. In this question, there is a program given. Okay, there is a program given. In that program, you can see that there are three columns. The first column states the instruction, which is a part of the program. And the second column states that the operation that is going to be performed when that instruction gets executed. And the third column states that the number of words that are required for this instruction in main memory. Okay, so this is the thing. The program is just all about 1, 2, 3, 4, 5, 6, 7, 8 instructions, in which when each of the instruction gets executed, the corresponding operation is going to be performed, which is stated in the operation column. Okay, so here it goes. There are three users registers, R1, R2, and R3. Okay, here in the program, it is given that there are three users registers, R1, R2, and R3. Okay, and here, what is going to happen when this program gets executed? First of all, we'll look at the questions. Okay, so let me again copy the question from the net. Yeah, this is the question. Let us see. Here some of the terms are repeated. Let me remove those redundant terms. Yeah, here is the question. Now let us stay focused on this question. Okay, now see, assume that the contents of the memory location is 3000. Sorry, contents of the memory location 3000 is 10 and the contents of the register R3 is 2000. The contents of each of the memory locations from 2000 to 2010 is 100. Okay, the program is loaded from the memory location 1000. All the numbers are in decimal. Assume that the memory is word addressable. The number of memory references for accessing the data in executing the program completely is what? This is the actual question. Let us see. Okay, now first of all, in order to answer this question, we should be able to understand the program. Here in this question, he asked, after we execute the program, how many memory accesses are actually required? You know, in executing this program, how many memory accesses are actually required? This is the question. Okay, so for this, we need to look at this question in detail. Okay. Yeah, this is the question. Now we need to understand here how many times the memory will be accessed. This is the very question that is asked in what you call as a first question. Let us see how many memory access are actually required here. So here you can see that when you look at the operation for every instruction, the operation will state the operation that is going to be performed during the execution cycle of that instruction, right? So here when you execute the first instruction from the memory 3000, the data will get transferred to R1, right? Yes or no? When we execute the first instruction from the memory location 3000, the content will get transferred to R1. This is the first instruction. So the first instruction leads to one memory access, right? This first instruction leads to one memory access. Okay. Now, second instruction also, you can clearly see that move R2, R3. But R3 is in brackets. That means that a memory of R3 will get transferred to R2. Here the operation itself, it states that it's a memory transfer, which means that memory of R3 has an address. Taking that address will go to the main memory. From that location, the content will get transferred to R2. This also is another memory access, right? It is the second memory access. Okay. When you look at the third instruction, you would understand that there are no memory accesses. Add R2, R1 plainly stands that R2 and R1 will get added and finally gets transferred to R2, which is also stated in the operation field, right? So here again, the very next instruction also, if you can have a look at, has a memory access in which R2 will get transferred to memory of R3, which is given in the description of the instruction, which means that it also leads to one memory access. Okay, and rest of the instructions, if you can have a look at, there are no memory access in it. Once again, we do have three memory accesses and you would get them the moment you understand each and every instruction. First instruction requires a memory access because the contents from the memory location 3000 will get transferred to R1. Okay, so which leads to one memory access. Second instruction also has a memory access. Because it is another memory access and the third memory access. And now the total number of memory access will be equal to these two plus this is 1. Got me? Which means that there are three memory access. But if you can have a look at the program, one instruction is outside the loop. Two instructions are within the loop, right? For these two instructions, we need to find out how many number of the loop is going to get repeated. You can clearly see that the loop gets repeated for 10 times. Loop is based on R1's value. the moment R1 is equal to 0. When the moment R1 is equal to 0, the loop gets terminated, right? Okay, when the moment loop gets terminated, then what will happen? The program gets executed finally and finished. So we need to understand how many times the loop gets repeated, which is based on R1. If you look at the program, R1 is equal to 10. Why R1 is equal to 10? Here in the very first instruction, the memory of 3000 will get transferred to R1, and the memory of 3000 is given in the question is 10. So the loop gets repeated for 10 times. So 10 into 2 is equal to 20. 20 plus 1 access, memory access outside the loop, which is equal to 21. That's it. So let me look at, oh, you people already got it. Very good. You people already got it. So I'll be very happy. So let me see. What is the next question? We will find out what is the next question. Good. Did you get it? Why it is 20? Kirti, did you understand why the answer is 20? Sorry, 21? Or should I explain it again? Should I repeat it again? Very good. Okay. I will explain you once again. First, you stay focused. Already that guy has got it. Sure. I'm going to explain it again. Stay focused here. Now we are asked, how many times the memory will be accessed, right? This is the question. There is no, it is not a hidden question. It is a plain and open question. And there are no tricks and tails in it. Twists and tails in it. And there are no tricks absolutely also are there in the question. Simply we are asked, how many times the programmer needs to access main memory as he is executing the program, right? Yeah. We will see how many times he is going to access the main memory. Okay. For that, let me clear this once again. Yeah. This is the program. We will see how many times we are needed to access main memory. The first instruction requires a memory access. If you can have a look at. Yes or no? That is, this is the first instruction in which we can clearly see a memory access. How this instruction is going to get executed, stay focused. Move R1 comma memory of 3000 means that in the main memory there is a location 3000. Okay. In the memory location 3000 there is a value. Okay, let us say it could be 150. The purpose of this instruction, that the meaning of this instruction execution is, from the memory location 3000 the content should get transferred to R1. R1 is a processor's register. So what will happen? From the memory location 3000 the contents 150 will get transferred to R1. Generally, actually the value of 3000 is not 150, it is different, but for an example I am telling you that memory 3000 at memory location 3000 we do have a value which is equal to 150. Then 150 will get transferred from memory to R1, which is a memory access, right? Yes, it is a memory access. Here we have a memory access. When we do have a memory access, next to that instruction I am putting M. M stands for it's a memory access. This instruction has a memory access. Okay. Now here when you have a look at, this instruction also has a memory access. For that we need to understand what happens when this instruction gets executed. This instruction simply moves the contents in between R2 and R3. But how? Let us stay focused. Let us say that R3 is equal to, let us say, 450. Okay. If there is an instruction move R2 comma R3, if there is an instruction move R2 comma R3, then that means that the contents of R3 will directly get transferred to R2. But this instruction is not simply move R2 comma R3. If you can see, this R3 is enclosed in brackets, right? Yes or no? So this brackets means that it's a memory access. This 450, when the R3 is kept in brackets, means that is a memory address. It is not a direct value. But when you, as you can see in the instruction, this R3 is kept in brackets, which means that the contents of R3 is a memory address, not a direct value. So what we need to do is we just have to go to R3, then we'll access the main memory, taking that address. Main memory will be accessed, in which there will be some value. That value will get transferred to R2, which is the exact meaning of move R2 comma R3. The memory of R3 will get transferred to R2. So this is significance. Here also, as you can see, we do have one more memory access. This is the first memory access and this is the second memory access. Okay. And the third one is, as you can see, this instruction doesn't have any memory access. This instruction simply is an addition in between R2 and R1. Finally, the contents will get transferred to R2. Okay, the result of this addition will get transferred to R2. Okay, now look at the next subsequent instruction, which is the fourth instruction. Here R2 comma R3. If it is simply, as you know, that R3 comma R2, then the contents of R2 will directly get transferred to R3. But here it is different. R2 is not directly getting transferred to R3. Rather, R2 is getting transferred to the address which is there in R3. Okay, so we'll go to R3. R3 is 450. Let us say R2 content is 500. This 500 will get transferred to memory of R3, which means that this 500 will get transferred to 450th location. It is going to replace the element which is available at 450 by the value of R2, which is equal to 500. You got me? Once again, let me explain it. The contents of R2 will needed to be transferred. Where? Not into R3. R3 will give you a memory address. To that memory address, contents of R2 will get transferred. Here first we'll see what is the R2 value. R2 value is equal to 500. Taking this value, we will go to R3. R3 gives us an address. Taking this address, we will access main memory. Under this address, the value of R2, which is equal to 500, will be placed. Okay, so this is it. As you can see that so far we found out that 3 of the instruction in the program are having memory accesses. The rest of all the instructions don't have any memory access. Only 3 instructions has memory access. The question is exactly the same. For how many times the memory will be accessed when you execute this program? Okay, so 3 times. But hold on, there is a twist here. Looking at that question, we can see that there is a loop. Did you get it? When you look at the question, you can see that some instructions are within the loop. If any memory access that are inside the loop will be multiplied by the number of times loop gets repeated. If the loop gets repeated for 100 times, then if I do have 2 memory access within the loop, then the number of times memory will be accessed is 2 into 100 will be equal to 200. For that, we need to see for how many times the loop is getting repeated. Okay. When you look at the question carefully, loop gets terminated on the value of R1. Okay. Here, the final instruction to end the loop is DEC R1. That is decrement R1. Did you get it? So when we decrement R1 is equal to R1 minus 1. Then a conditional statement is going to get executed, that is B and Z loop. Branch on non-zero, we will go to the loop, we'll go to the label loop. Okay, if the value is equal to non-zero, we will go back to loop. If the value is equal to 0, then we will terminate. Okay, if the R1 value is equal to 0, loop gets terminated. If the R1 value is not equal to 0, loop won't get terminated. So based on R1's value, the number of times the loop gets repeated will be decided. So what is R1 value? We need to find out. So see, we'll see and we will have a look at the question to find out what is R1. What is R1's value. Okay, here read the question. Assume that the contents of the memory location 3000 is 10. So let us say that there is a memory location 3000 in which the value is equal to 10. Okay, and the contents of the register R3 is equal to 3000. There is a R3 register. The R3 register is equal to 3000. Okay, the contents of each of the memory locations from 2000 to 2010 is 100. So again, in the main memory, from 2000 to 2010, 2000, 1, 2, 3, 4, 5, 6, so on, let us say 10. This is 2000. This is 2010, let us say. Each of these memory locations value is 100 as given in the question. Okay. This is 2000, this is 2010. Okay, and the program is loaded from the memory location 1000. The program, this program is available from the memory location 1000. The starting address of the program is 1000, which is as given in the question. Assume that the memory is word addressable, it's not a byte addressable. Fine. The number of memory references for accessing the data in executing the program completely is. These are the complete details which are given in the question. So here we are not provided with R1's value. R1's value is not given in the question. So for that we need to have a look at the program. In the program, R1 value might have been initialized. Of course, when you look at the first instruction, you can see that the R1 value will be initialized. How? The memory of 3000 will be transferred to R1. Did you get it? Initially, R1 value is nothing. Nothing is given for R1's value. So what we need to do is we just have a look at the program. When we look at the program, we understand that R1 is initialized with the value of the memory of 3000. So we need to understand what is memory of 3000. Are we given? Yes. This is memory of 3000. This is the memory location 3000 under which we got a value which is equal to 10. Okay. So obviously R1 value will be equal to 10 because in the program we found out that the memory of 3000 will get transferred to R1. Okay. So obviously R1 value is equal to 10. Which means that the loop gets repeated for 10 times. Did you get it? Loop gets repeated for 10 times. When the loop gets repeated for 10 times, the memory access within the loop will be multiplied by 10. So 10 into 2. Within the loop, I do have 2 memory access. Outside the loop, I do have 1 memory access. 10 into 2 is equal to 20. Yes or no? And outside the loop, I do have a single memory access. As it is not in the loop, inside the loop, I don't have any problem. This memory access is a single memory access. But within the loop, I do have 2 memory access. And the loop is being repeated for 10 times. So 2 into 10 is equal to 20. So the total memory access are equal to 21. Did I make it myself clear? Okay. So this is, how you have to solve this question. So what I expect from you guys is, I want you people to solve the remaining 2 questions which are given based on the same data. Now, did you copy the question from internet? Did you copy the question from internet, or you want me to present that question on the screen? How this instruction size is too? Okay, Lokesh, I will put it this way. So far good. You people are following. You people are able to answer everything that I ask. I put it this way. What you do is you just do a research. Okay, that is, I mean, there is a third column. There is a third column. In this third column, he is talking about the size of the instruction. Right? The size of the instruction is variable in this case, as you can see. Some instruction size is equal to just one word. Some instruction size is equal to 2 words. Right? Am I right or not? Am I right or not? So you just, before solving the question, you just try to understand it. If you can't solve, anyhow, I am there to explain you guys. If you can't solve this question, I am there to explain you guys. I hope I make it myself clear. So if you want to explain me, if you want me to explain you right now here, I will do it. But I just want you people to give a try. Will you or not? But you just don't come back without giving a try. Tell me if you want me to explain you this. I will do it. This is what exactly I want from you guys. So there are two questions. One question is already explained here. Second question on the same data is, assume that the memory is word addressable. Assume that the memory is word addressable. After the execution of this program, the contents of, what is the content of the memory location 2010, right? And you can ask me, and my mail ID also I gave it to you guys. Okay, so try it out today itself. Try it out today itself. I don't have any Telegram channel, just I do have a mail ID. You can mail me to anilvarsha.in@gmail.com. I will write it here. Yeah, I want you people to do it right after this session. You people have to try. The first question is all about the value of the memory location 2010 after you execute this program. The second question is all about what is the return address? That is, when in INC R3 is being executed, if there comes an interrupt, what will be the return address pushed into the stack? Yeah, sure. Here, stay focused. For 20-second question, you don't know what is interrupt, right? The interrupt concept hasn't been discussed yet. Interrupt concept will take some time because that comes under secondary memory, secondary storage. So 20-second question I will redesign, okay, for you guys. The 20-second question you write it as, what is the program counter value for INC R3? Write it down. Yeah, sure. Kirti S. Kumar, you can mail me anytime. Right, I'm absolutely available for you guys all the time. What do you call 24 hours a day, 365 or 360 days round the year. Okay. When you have it out, you just ping me through the mail. Fine. Let me once again reframe this question. That is 20-second, not 20-second question. The third question on the same data. Third question on the same data is all about what will be the program counter value for INC R3. What is the program counter value for the instruction INC R3? Did you get it? Yeah. This is what the question is all about. the third question on the same data. If you could solve this, I will be very happy, so that I will be able to get you people to the next and foremost topics. Okay, so what we'll do is we will end the session here exactly. Next week, what I'll do is I'll completely reserve the next week's session only for the gate questions, because we are done enough in processor, at least in the register part. So we will be able to solve some of the questions seriously when it comes to the registers and their organizations, and instructions and their sizes, programs and the purpose of the program's executions. So the next week I will completely reserve it for the gate questions and their solutions. Okay, so this is what the session is all about. Next week we'll meet again, same day, same time. Okay, thank you so much.